Hello, everyone. Good morning, afternoon, or evening. Dear authors and invited guests, welcome to Technical Session 9E. Myself, Sirali Gaur, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GIA Scholastic, it is my great pleasure to welcome you to the 10th World Conference on Information Communication Systems, Software Security and Sustainability, World S4 2026, London, UK. The 10th edition of the conference is being organized in a hybrid mode. The physical event was held yesterday in London, UK, and the virtual event is being held through Zoom from 29 to 30th July 2026. I hope you will enjoy the knowledgeable and interactive sessions through the day. In this session, we have a total of 6 presentations. Each presenter will be given 12 minutes for their presentations and 3 minutes for question and answers. I will raise a gentle reminder when the presenter crosses the 10-minute mark. There is another request to all the participants that you stay connected with us till the closing remarks. If you have any query or any updates, you can write to me in the chat box. Just before we start the session, I would like to introduce you all to the chair for this session. Dr. Namdev M. Sawant. Dr. Namdev is an IQAC coordinator and assistant professor in the Computer Science and Engineering Department at SKN Singad College of Engineering, SKNSOSCOE, Maharashtra, India. He specializes in areas like information security, blockchain, cloud computing, and high performance computing. I welcome you, sir. Would you like to share any words before we start?
No, ma'am. Let us, without wasting much of the time, we will start. So, first of all, I welcome all the participants, and I wish all the best for your presentation. The way you have did. So, just from my side, there is one requirement. Please follow the guidelines and please complete your presentation within a time. The time allocation is already 15 minutes is given. Out of that, 12 minutes is for presentation and 3 minutes is for question and answer and discussions. So we will summarize the session at the end. So over to you, ma'am.
Thank you so much, sir.
Yeah.
For our first presenter today, we have Pranali Pawar with the paper title A Federated Intrusion Detection Framework for Distributed Network Security. Dear presenter, you may start presenting.
I'll share the screen just one minute.
Yes, ma'am.
Is it visible now?
Yes, ma'am.
Okay, good afternoon, everyone. I'm Pranali Pawar, and my presentation of work is the Federated Intrusion Detection Framework for the Distributed Network Security. So, this research focuses on the developing the privacy and preserving intrusion detection system using the federated learning. The proposed framework enables the multiple organization to collaboratively train the intrusion detection model without sharing the sensitive network data, thereby improving both the security and the privacy. So, the background and network evaluation with the rapid growth of cloud computing, IoT, and the enterprise networks, the cyber threats have become a more sophisticated and distributed. So, the traditional security mechanisms struggle to analyze the massive amount of network traffic generated across the multiple domains. So, therefore, the modern networks require the scalable intelligence and privacy preserving model, that is nothing but the intrusion detection system, that can effectively identify the malicious activity without exposing the sensitive information. So the centralized problem is that the traditional intrusion detection system collect the network traffic from the multiple locations into the centralized server. We can collect the data from the hospital also, some government offices also. So although this approaches simplifies the analysis, and it introduces the several challenges. First, transmitting the raw network data increases the risk and privacy breaches. Second is centralized system creates the communication overhead and the high latency. Finally, a centralized server become a single point of failure and reducing the overall robust of the system. So, my proposed framework is to privacy conscious design, collinear model training, global model aggregation, and adaptive strategies. So, uh, uh, the proposed framework addresses these limitations using the federated learning. So each participating organization trains the intrusion detection model locally using its own data. Only the model parameter, all the aggregate are shared with the central server instead of the raw traffic network. So the several aggregate these updates to create a global model and send it back to all the participant nodes. So this collaboratively learned approach preserves the privacy while improving the detection performance. So there are two nodes, distributed local nodes and the central aggregator. Uh, and the architecture consists of multiple distributed local nodes and the central aggregation server. So each local node independently monitor the network traffic and train its local intrusion detector model. So after local training, only the updated model parameters are transmitted to the central server. So the central server aggregates all update to generate a global model. So which is redistributed to every nodes for the next training round. So first we train the model, then we test the model by the system architecture. Uh, Local model training, the intrusion detection model using the local network traffic, the model is optimized using the iterative gradient based learning. The hybrid loss function is employed to balance the three objective: accuracy attack classification, effectively anomaly detection, and reduce the model complexity. So these parameters we keep it in mind. So this enables each local model to adapt to the characteristics of its own network traffic. Then a federated aggregation model, every node send only the updated model parameters to the central server. So the server combine all this updated using the adaptive aggregation strategy, where the nodes contributing the higher quality updates receives the greater weight, and this produces a more accurate global model while ensuring that the raw network data never leaves the local organization. uh, uh, in the privacy is the key advantage of our framework. So before the model update are transmitted, they they are encrypted using the secure aggregation technique. So additionally, carefully control the mathematical noise is added to the updates to prevent the gradient interference attack. So this combines the protect confidential network information while maintaining the high detection accuracy. So in dynamic privacy mechanism, each node is assigned a dynamic privacy budget based on the sensitivity of the model updates. So instead of relying on the single noise distribution, the framework combines the Gaussian and the Laplace noise to provide the stronger privacy protection while minimizing the impact of the model performance. So for the experiment setup, were conducted using the benchmark intrusion detection database. Then this database contains both the normal traffic and the multiple categories of the cyber attacks. So the database where the partition across the several distributed nodes to simulate the real world federated learning conditions. The processing and the evaluation, the underweight pre-processing, including the categorical encoding, feature scaling, data partitioning. The model performance was evaluated using the standard matrices such as accuracy, precision, false positive rate, etc. The communication efficiency across the multiple federated round was also resolved by using this. The results and key findings contains the detection accuracy, communication overweight, privacy resilience. So the purpose of this framework is achieve the competitive intrusion detection accuracy while significantly reduced the communication overhead because only the model updates were transmitted. Furthermore, a hybrid privacy mechanism was successfully protected sensitive information against the interference attacks and demonstrating the effective balance in between the privacy and the detection performance. If we see the convergence analysis for the federated learning processes, so during the initial communication round, the model rapidly improves as the knowledge from the multiple participants are combined. So after the several rounds, the learning process is stabilized. So it indicates that the global model has coverage successfully. The impact of privacy on performance, the trade-off between the privacy and detection accuracy, as the privacy protection becomes stronger by increasing the uh, perturbation, the detection accuracy decreases slightly. So this shows that the purpose frameworks maintain the excellence utility while ensuring the stronger privacy preservation. So this federated intrusion detection framework that enables the collaboratively intrusion detection without sharing the sensitive network data. So the framework combined the adaptive federated aggregation with the privacy preserving mechanism to achieve the secure, scalable, effective distributed intrusion detection. So this future framework include the integrating the blockchain for the trusted aggregation, defending against the attacks, and deploying the framework in the real world age and the IoT environment. Thank you.
Participant, anybody want to ask any question? Okay, if there is no question, so nice presentation, Pranali.
Okay. Thank you, sir.
I have one question.
Yes.
So, as you have shown the privacy and your accuracy trade-off.
Yes, sir.
So, as you are increasing the privacy, the accuracy is going to decrease. Is it correct?
I'll check that. Just 1 minute.
Hello.
Increasing the privacy, accuracy decreases. Yes, sir.
Yeah. So, have you find out the threshold value? How where actually we should be stop, or where we should be, which will help that threshold value, where the privacy is also good and accuracy is also good.
Uh,
Have you find out that threshold?
Not yet, sir, but I'll think on it.
Okay, okay. ठीक है.
Okay,
ठीक है, ठीक है. Thank you, thank you.
okay, sir. Thank you.
Thank you so much for that presentation.
Thank you, ma'am.
Now we have Srinidhi GA with the paper title Adaptive Objective Hospital Capacity Management During Pandemic Surges, a Hybrid Deep Learning and Optimization Framework. Dear presenter, you may start presenting.
Okay. Good afternoon, good evening. I don't know what is the timings there. Thank you so much for the opportunity. I would like to present my paper titled An Adaptive Multi-Objective Hospital Capacity Management During Pandemic Surges. This is with respect to deep learning approaches and optimization framework. Basically, the concept got originated just because we had a lot of unpredictable demand with respect to the utilization of beds and utilization of a lot of hospital resources, which were having a lot of problems, particularly in the developing nations like India. Okay, this unpredictable demand surges, so that it may be with respect to the pressures on beds, staffing, and equipment, and beyond the system thresholds. The some of the challenges over here is that the numbers are very much what do you call alarming, because of the inadequate planning methods and competing objectives, and there is a lot of demand uncertainty. So because of that, we thought of going ahead and propose a method wherein we can be utilizing the optimal resources within the available resources. So here, when we went through the literature review, there were a lot of algorithms, or I can just say proposals, which were over there. But some four of them have been taken up and listed in the paper as well. The first one is MILP, which is again this is theoretically sound, but poor scalability and cannot model the nonlinear demands. When it comes to SVR, again, it uses a machine learning approach with low MAPE, and it is between 0.49 to 4.1%, limited to single step prediction and no multiple objective support. The third one that we used for we went through was random forest method. Again, it ensembles the machine learning process with 17% over time series baselines, and we have the gradient boosting that we directly say it as GBs, which is having consistent accuracy but extensive tuning required, no multiple objective capabilities. So overall, there is a research gap over here, which we coined like no existing approach simultaneously handled multiple objective optimization and temporal demand modeling and real world operational constraints. Okay, so with that, we came up with a new idea wherein we came up with three major categories. One is demand forecasting, optimization engine, and decision support. So here we have LSTM networks for demand forecasting. Here we had somewhere around 25 features and 7 days forecast it was able to do. And we have optimization engine by using MOPSO algorithm with 4 objectives based upon the bed capacity and staffing limitations as well, considering the constraints as well. And the decision support, wherein it helps the admin interface and real-time recommendations. So it is again operational for example, ICO assignment or staffing planning, etc. And we do have these things in a greater detail. So for the first step, the demand forecasting, we have bidirectional LSTM that we have used. We have taken up 25 engineered features from with 7 days of 7 days ahead predictions that were possible, and we had this optimization engine, which is going to give us 4 competing objective functions that especially with respect to optimal solution repositories and bed capacity and staffing constraints and near real time convergence. Okay. And decision support, admin interface, again, real time front display, actionable staffing and bed plans, institution specific priority tuning, and also continuous model retraining as well. So for this, the LSTM architecture demand forecasting module, wherein we had 25 features which were existing in the EHR records, that is electronic health records, and census data with respect to seasonal indicators and incidence rates as well. Here as I have told you, that we have used bidirectional LSTM in 2 layers. One is 64 units with the drop off of 0.3, and they appear to be bidirectional, which is governed by the equation which has been provided. Again, in the second layer, that is second layer by LSTM, again 64 units with a dropout 0.3, with which extracts higher order patterns with respect to the things. So output layer for this, we had a kth day, that is demand forecast, which was done by using y cap of t plus k, which will be governed by this equation. And when it comes to multiple objectives, the first objective is minimize patient overflow. The second one was minimize surge activation cost, then maximize bed utilization and minimize the staffing penalties. So this was done by using MOPSO algorithm, wherein the algorithm flows like this in 5 stages. Initialize particles form with feasible solutions, evaluate 4 objectives for each particles, and then update the Pareto optimal solution repository. The repository, once it is updated, the inputs will be coming for the next stages in the same manner. So adapt velocity based upon the exploration and exploitation. Then the output will be the front for the admin selections. So the experiment settled was for this was taken for the US clients. As you can see, the first and the last author for this paper are from San Francisco. They are students. They were used to collect the almost like 2.3 million patient records, and this has happened in the span of 18 months, the data span, because a lot of regulatory processes. So the outcome was a bit late. So for the duration of 18 months, and 5 major US health systems were considered, out of which 12 data, if at all, if we are 18 we were considering. So based upon the baseline algorithm compared MIPL, SVR, and random forest and grid boosting. So the results that we had shows us that we have improvements with respect to traditional MILP, that is 88.8% of improvement, 61.9% improvement with respect to when we compare it with SVR, and 50% improvement with respect to uh, the gradient boost. So thereafter, when it comes to bed utilization efficiency, we had 94.7%, which was the highest. So we had the baselines with respect to MIPL. We had 18.3% increase. With respect to SVR, it is 12.6% increase. With respect to the RF, it is 10 point random forest, that is 10.5%, and with respect to GB, it is 9.9%. Okay, and next comparative study which we did with respect to emergency department waiting time. The emergency department waiting time has been drastically reduced within 6 weeks. As we can see, the proposed algorithm is the least with the green line over here. And with respect to optimal cost savings, it has saved almost 38.9% of operational costs, with more accurate demand forecasting, optimal resource allocation, and improved bed utilization rates. So multi-objective uh, performance comparison, of course, it is the only algorithm that had this uh, multiple objective performance was our AMCM, that is the proposed algorithm. So what is the it is temporal modeling, genuine multi-objectivity, and operational realism. Because in the first case, we have used BiLSTM architecture, which captures complex nonlinear session dependencies and multiple scale demand patterns that is having simpler statistical methods fundamentally, which cannot be represented. and genuine multi-objectivity. It is, of course. At the same time, we have some limitations as well. Validation on US hospital system, which was very rigorous, and it is in the process. We are trying to get it done. And we have patient heterogeneity that has not been incorporated, and that we keep ourselves for the upcoming research direction. And real-time EHR integration remains to be implemented for continuous updating, because we had the patterns which were already there, and we have just collected it. However, the system does not incorporate the real-time EHR integration, so that once there is a changes in the EHR, the pattern should again start changing. So, in the conclusions, we have the forecasting error has drastically reduced by 0.8%. Bed utilization efficiency has increased to up to 94.7%. Waiting time reduction, that too in the emergencies, it is 42.3% reduction. And operational cost savings, it is 38.9%. So this has been validated on 2.3 million real patient records across 5 health systems, the largest evaluation. And simultaneously, it improves the patient outcomes, reduces the operational cost, etc. Provides health administrators with a lot of advantages. So I think that's from my end.
Thank you so much. Do we have any questions?
Okay, the nice presentation.
Thank you.
Any audience participant, do you have any question? Okay. So if there is no question, madam, can we go for the next presentation?
Yes, sir.
Yeah,
Thank you.
please.
Next, we have Nwagu Chima with the paper title AI-based Academic Integrity Detection Systems in Higher Education, a systematic review of construct validity. Dear presenter, you may start presenting. Dear presenter, you are muted.
Good morning, good afternoon, good evening, everyone. My name is Nwagochima Ajanwachuku. So today I will be presenting our paper titled AI-based Academic Integrity Detection System in Higher Education, a systematic review of constructs validity. So the central question our research is asking is just simple. Question is, when AI system flag plagiarism, AI-generated writing, or suspicious behavior, are they truly detecting misconduct, or are they detecting proxy signals that still require human interpretation, that still requires interpretation by humans or institutions? That is just the question our research is asking. So before discussing the study or the research, I will briefly outline the presentation. I will begin with the measurement problem that motivated this review. Then I'll present the research aim and methodology. Then next, I will summarize the detection systems that were reviewed, followed by the 3 main findings in our research. Then I'll introduce our proposed proxy measurement risk model before concluding with the policy implication and recommendation. So we start with the measurement problem. We see we are conversant that universities now use AI tools to compare student submissions. They use AI tools to estimate whether text was AI generated. They use AI tool to identify unusual exam behavior in terms of proctoring examinations. And they also use AI tool to verify students' identity. But academic misconduct is not only a pattern in data. It's more than that. It is contextual and policy based. So a system may detect a useful signal, but the system does not automatically prove misconduct. It still requires interpretation. The aim of this research is to examine how AI-based academic integrity detection systems operationalize, measure, and validate academic misconduct in higher education. So our study is guided by 5 research questions. The first research question is, what system types are evaluated? The second research question is, what signals do they measure? The third, how do these signals align with misconduct constructs? Fourth, which validation evidence is used? And fifth, what construct validity gaps exist? So in simple terms, our study does not only ask whether these systems work technically. No, the systems do work technically. So we are not just asking whether the system works technically. We're asking whether the operationalized measures correspond to the academic misconduct constructs that they claim to detect. Now, our methodology. For our methodology, we used the PRISMA approach. The PRISMA approach for our methodology. Our search covered ACM Digital Library, the IEEE Explore, Web of Science, and Google Scholar. During our initial search, we identified 793 records. And after removing 60 duplicates, we were left with 733 records, which were screened. The 90 articles were assessed for eligibility based on the eligibility criteria, the inclusion and exclusion criteria. And at the end of the exclusion or assessments, 56 studies were finally included in our study. We're included in our study. So our findings were synthesized narratively following the SWIM approach, that is the synthesis without meta-analysis approach. Now, the reviewed studies covered several academic settings, and this included essay-based coursework, programming assignments, online examinations, and thesis evaluation. So we found out that the largest category were AI-generated content detection with 19 studies, and plagiarism detection with 16 studies. Then we had behavioral monitoring, that is 8 studies, and other categories like authorship verification, multimodal detection, and biometric authentication. But something was common across these categories. The common pattern was that these detection systems, they measured observable digital traces, and then they used those traces to infer broader misconduct constructs. They use those traces to infer broader misconduct constructs. Then our findings, the main finding one is that the systems, they measure proxies. The detection systems measure proxies. All 56 reviewed studies measured observable digital signals, and these signals include similarity scores, classifier probabilities, behavioral logs, biometric indicators, feature vectors, stylometric features, and anomaly metrics. You see, yes, the fact remains that yes, these signals may be useful, but they are useful as risk indicators because, but they do not directly capture things like intent of the students or the user, disclosure, they do not capture disclosure, policy alignment, no, legitimate collaboration, they don't capture this, or assessment conditions. And these things I just mentioned are involved in academic misconduct. These are academic misconduct. Intent of the student, disclosure, policy alignment, legitimate collaboration or assessment. But these detection systems do not capture these things. The main finding, number two, is that there were a lot of construct misalignments. 55 or 56 studies showed evidence of construct misalignment. Many studies treated similarity scores as plagiarism. They treated AI generation probability as dishonesty, and behavioral anomalies, they treated it as cheating. You see, these inferences may be useful for screening, but they cannot by themselves prove misconduct. So a risk signal becomes very dangerous when it is treated as proof. Then the third finding is technical validation dominates. Most studies validated their systems using the technical metrics such as accuracy, precision, recall, F1 score. That was what they used. You see that in our review, 43 of the 56 studies that we reviewed, they relied on performance metrics, while only three studies directly addressed construct validity. Fewer studies examined bias and robustness, and 47 studies relied on proxy ground truth rather than real misconduct cases. So the problem is that accuracy measures classification performance, but it does not prove that the measured signal captures academic misconduct. A system can classify a proxy accurately and still provide weak evidence of misconduct. So our paper proposes a proxy measurement risk model. The model evaluates 5 dimensions. These dimensions are 1, signal relevance, construct coverage, contextual sensitivity, decision consequence, and validation evidence. So this dimension help judge how far the measured signal is from the misconduct construct being inferred. So based on that distance, the risk can be classified as low, moderate, or high. So this will help institutions decide whether a detection output should be used only for screening or for further investigation or for high-stake disciplinary actions. Then, in conclusion, our review shows that the current AI-based academic integrity detection systems, they are mainly signal detection systems. Yes, they can identify patterns that may raise concern, but they do not fully capture intents of the users, the students. They don't capture disclosure. They don't capture collaboration context. They don't even capture institutional policy, assessment condition, or legitimate academic practice. So the practical implication is that AI outputs should be used as screening evidence. supported by human judgments, student explanation, and policy context. So detection scores from these AI systems should not be treated as automatic proof of misconduct. Thank you. Thank you.
Thank you for your presentation.
Thank you so much. Do we have any questions?
So I have one question. What are your recommendation for future research in this area? Can you elaborate within 1 to 2 minutes? Hello, am I
Sorry,
audible?
please. Yes, I was muted.
Oh,
Sorry. So my
yeah, yeah.
future direction, my recommendation is that future researchers should build AI systems that that can capture student intent, that can capture collaboration context, that can capture institutional policy, that can capture assessment condition, and also capture legitimate academic practices. And yes, that is my recommendation. And institutions should not just use, I think there should be more research on how institution uses AI to the broader sense of how institution use AI detection to when it comes to policy decisions.
Okay, okay, okay. Thank you. Thank you.
All right.
Thank you so much. You may stop presenting your screen now. Now we have Nguyen Huynh with the paper title Application of Global Positioning System, Software for Surveying, Mapping and Establishing a Photo Interpretation course in Thuan and Ward, Ho Chi Minh City, 2025, Vietnam. Dear presenter, you may start presenting. Do we have any of the other authors present?
I can present.
Okay, you may start presenting now.
Okay.
Now we have Rebecca Hufke with the paper title Improve Protein Sidechain Angle Prediction Using Optimized Transformer Architecture. Dear presenter, you may start presenting.
Okay. Can you hear me?
Yes, ma'am.
Okay. Hello, everyone. I'll be presenting my research on improved protein sidechain angle prediction using optimized transformer architecture. Firstly, I would like to highlight the importance of proteins and their role. Proteins are molecules that carry out essential roles in the cell, such as transport and helping the immune system. Proteins are made up of smaller units known as amino acids, which are connected by peptide bonds to form a sequence. Each of these amino acids has a side chain that determines its chemical properties and behavior. Each amino acid, of which there are 20 different types, can be represented by a letter. Proteins can then be represented by a sequence of these letters, with each letter corresponding to an amino acid. The sequence determines the tertiary structure of the protein, also known as the 3D structure. The structure of a protein determines its function. Understanding this relationship is essential for drug discovery and disease analysis. There have been many methods to determine the structure of a protein. Experimental methods can be expensive, time-consuming, and resource-intensive. Traditional machine learning models, like SVMs, don't scale well for complex proteins. They also require manual feature engineering and struggle with long-range dependencies that are critical to protein folding. These challenges have led to more focus on deep learning approaches. These models are faster and able to capture the complexity of the structure and the relationships between amino acids. Deep learning models, specifically transformers, have shown significant improvements in predictions for proteins with complex structures. Transformers overcome these challenges with the use of their self-attention mechanisms, which allow these models to focus on different parts of the protein sequence to capture long-range dependencies. This is crucial for determining the structure. Transformers are more scalable than other models. Large-scale systems such as ASM-fold and AlphaFold have explored the application of transformers for protein structure prediction. Both models take in sequence data and produce a 3D structure of the protein, but they require extensive training and computational resources. Therefore, this research presents a lightweight transformer optimized to improve protein structure prediction by focusing specifically on predicting side chain angles that will construct the 3D structure using the Cas12 dataset. This work focuses on refining the existing transformer model provided by SideChainNet by exploring different architectural configurations, hyperparameters, regularization techniques, and inputs. The proposed system follows four main stages: data preparation, model design, improvement, and evaluation. The data preparation phase involved obtaining the dataset from the SideChainNet framework and cleaning and structuring the data into the appropriate format. The dataset contained a range of information about the proteins, such as the amino acid sequence, backbone and side chain angles, secondary structure and evolutionary information, and 3D coordinates. The Cas12 dataset was the primary dataset used for training and evaluation. The dataset contains proteins used in the Cas competition, which is a competition that aims to establish the state-of-art models for protein structure prediction. The dataset contained a diverse set of proteins with minimal overlap between splits. Each amino acid was tokenized into integer values. For example, alanine was mapped to 0 and cysteine to 1, so that the model can understand and process the sequence. To handle the missing angles, NaN values are replaced with 0.0. The tensor of angles was split into backbone and side chain angles. The side chain angles were trigonometrically transformed into sine and cosine representations, so that instead of directly predicting the angles, the model predicts the sine and cosine of each angle to avoid dealing with the wraparound at 360 degrees. The model design phase focused on building a transformer model to predict the side chain angles of a protein. The model can take in two possible input configurations. The first configuration only takes the protein sequence. The second is a single input tensor formed by concatenating the input sequence with the combined structural features. Structural features include the backbone angles, secondary structure, and evolutionary information. The input is passed to an embedding layer that converts the amino acid tokens into continuous learnable representation. Since there are two different input configurations, a linear layer is applied to project the model input to the correct model dimension. Positional encodings are added to give the model a sense of where each amino acid is in the sequence. The input with the added positional encodings is normalized and passed to the encoder. The encoder-only transformer architecture includes a multi-head attention layer, which allows the model to attend to multiple relationships between amino acid residues simultaneously, capturing both local and long-range interactions, and a feed-forward layer, which applies non-linear transformations to refine the representations learned by the self-attention layer. This enhances the model's ability to capture relationships within protein sequences. The final output is passed to a tan-H activation function, which constrains the predictions to the range of -1 and 1 to match the expected sine and cosine values of side chain angles. The output of the model is a set of predicted side chain angles for each amino acid in the protein sequence. The predicted angles are used to reconstruct the 3D structure of the protein, which can be visualized or evaluated against the true structure. This design formed the baseline model. The third stage focused on improving the model's robustness and performance through architectural refinements, regularization, and hyperparameter tuning. The architecture was refined by reducing the feed-forward and input dimensions for efficiency. The model's sequence embeddings dimensions were increased to capture richer amino acid relationships. The activation function was changed from ReLU to GeLU as it performs better in transformers and allows for a smoother gradient. The tables in this slide and the next slide are the values that were chosen for the improved model. Secondly, regularization techniques were applied to reduce overfitting. This included adding and tuning the value for the dropout layers and weight decay parameters. Hyperparameter tuning was performed, testing different combinations of learning rates, batch sizes, and dropout values. Early stopping was applied, and a plateau scheduler to dynamically control the learning rate based on the validation loss. These strategies were implemented to ensure stable convergence and improve the generalization of the model. The final stage was model evaluation, which assessed how accurately the model predicted protein structures. These were the evaluation metrics used. The main ones were root mean squared error, which measures the average magnitude of the error between predicted and actual values, root mean squared distance or deviation, which measures the average distance between equivalent atoms in two different protein structures. A lower value indicates that the structures are more closely aligned, and mean absolute error, which measures the average of the absolute difference between predicted and actual values. This is used to evaluate the error for each of the 6 sidechain angles. In total, 4 models were trained, 2 for the baseline and 2 for the optimized model. The best baseline model was the sequence-only model, and the best optimized was the additional features model. The table shows each of the 6 sidechain angles' mean absolute error. Chi angles describe how the side chain of an amino acid twists or rotates away from the protein backbone. Each amino acid can have up to 6 chi angles, depending on how long its side chain is. Chi 1 is the closest to the backbone, while chi 6 is the most distal, located furthest from the backbone of the protein. For the sidechain angle predictions, the sequence-only model performs slightly better. The important differences are highlighted. For Chi1, the sequence-only model achieves a lower error of 0.888, and the additional features model achieves an error of 1.651. Overall, the additional features model performed poorly, specifically for Chi1 and Chi5, with higher errors. Though both models showed potential, the overall accuracy was still relatively low, highlighting the need for optimization. With the model improvement changes mentioned earlier, the optimized model showed substantial improvements. When looking at individual sidechain angles, the optimized model achieved much lower errors. Chi1's error dropped to 0.278 radians for the sequence-only model and to 0.043 radians for the additional features model. Performance improves greatly for Chi3 to Chi6 for both models. This is a visualization of a target that was in the Cas12 dataset. The blue represents the sidechain angle that is the true sidechain angle, and the red is the predicted angles. This is for the baseline model. As you can see on the right, this is the improved model, and the predicted sidechain angle aligns more closely to the true sidechain angle. The sequence-only model improved its root mean squared distance from 3.3 to 1.86, and the additional features model improved from 3.36 to 1.41. This represents over 50% improvement in structural accuracy and more than a 70% reduction in root mean squared error. The results demonstrate that tuning the architecture and hyperparameters can substantially improve transformers for protein structure prediction. The additional features model, which originally performed worse, now became the best performing configuration after optimization, indicating that the structural features were useful once the model architecture was tuned properly. The baseline model's failure to leverage these additional features demonstrates that extra data is insufficient without the architectural depth required to map complex interactions. To conclude, the contributions presented through this research are optimization and benchmarking of transformer architecture parameters, achieving a 70% improvement over the sidechain net baseline. A comparative analysis of sequence-only versus feature-enriched inputs, demonstrating that backbone angles, secondary structure, and evolutionary information reduce root mean squared distance by 24%. The optimized model achieved results comparable to top-performing CASP-12 submissions and targets in the CASP-12 dataset. Future work includes predicting both backbone and sidechain angles. Thank you.
Thank you. Do we have any questions?
Yes, I have a question. First of
Yes.
all, thank you for the presentation. Can you highlight one limitation of your proposed model?
Can be like computationally expensive to train a transformer, especially for large protein sequences. And yeah, so it can be like computationally expensive. And since the additional features model requires secondary structures and backbone angles and evolutionary information, not all of that is always available. So it can be hard to get a better result if you don't have that information.
Okay, okay, thank you. Thank you.
Thank you so much. I would like to call Nguyen Huan again for the paper title Application of Global Positioning System Software for Surveying, Mapping, and Establishing a Photo Interpretation Course in Thuan An Ward, Ho Chi Minh City, 2025, Vietnam. Okay, with that, we are done with today's presentations. I would sincerely like to thank all our authors for their excellent presentations and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. On behalf of the team, we on behalf of the whole team, thank you for the support during the 10th version and all the previous 9 versions of the conference. We will be happy to have you in the 11th version in 2027. All the presenters would be getting the digital certificates through email within 2 working days. The publication will go live within 7 to 8 months. Kindly cooperate with the team of World S4 2026. And now I would like to thank our session chair, Professor Namdev Sawant. Thank you so much, sir, for being a part of this session. Would you like to conclude this session by saying anything?
Yeah, I really thanks to the organizing committee as well as all the presenters who have presented their work very nicely. And I once again congratulate to the GR Foundation who is continuously organizing very nice conferences. Thank you, ma'am. Thank you. Over to you.
Thank you, sir. This is a small token of appreciation from behalf of the team of World S4 2026 and Global Knowledge Research Foundation and partners. Thank you so much for your valuable presence. Before we all leave, I would request everyone to switch their cameras on for a virtual snapshot, please. Thank you so much, everyone. Stay safe and take care.